Hello, everyone. So today's lesson will be on ionization energy and how you can calculate ionization energy from the convergence limit. First question, what is an ion? An ion is basically an atom that has gained or lost electrons. We know that a neutral atom has a certain number of protons that determines what the identity of that atom is, right? And whatever number of protons it also has that many electrons. So for example, helium has 2 protons and 2 electrons. So +2, -2 cancels out. It's neutral, right? But what if helium gains an electron, now has an extra negative charge, and that is known as an anion, a negatively charged atom. What if helium loses an electron? Now it has 2 protons, but only 1 electron. So now helium has a +1 charge. It's an ion with a positive charge, also known as a cation. So what it means to ionize an atom, though you might think we're talking about making, though you might think it might mean to make either positive ion or a negative ion, in this context, ionizing an atom means to remove an electron from it. All right, so at the end of the lesson, you should be able to understand how in an emission spectrum, the limit of convergence at higher frequencies corresponds to the first ionization energy. And you'll be able to calculate problems of how much energy is required to ionize a certain atom. Right, so over here, what we have is a beryllium atom, right? Beryllium has atomic number 4, so there's 4 protons in here in the nucleus, and there's 4 electrons, 2 on the first energy level, 2 more on the second level. Right, so first ionization energy. It is the energy it is the amount of energy you would need to remove 1 mole of the first valence electron in an atom from its gaseous state. Meaning, if you have, say, beryllium and it's its gas form, how much energy do you need to put in to remove a certain number of valence electrons from it, right? We're not going to worry too much about what a mole means. A mole is a numerical value, just like a dozen means 12. A mole is a certain number of electrons. So here, in this equation, we have beryllium in its gas form, right? And then it's ionized. It becomes a positive ion of beryllium because it's lost an electron, right? So how much energy was required to take this electron away from beryllium? That's its first ionization energy. As a reminder, valence electrons are electrons on the outer energy level. So this atom has 2 valence electrons because on the second energy level, this valence shell has 2 electrons. So let's see. So we have beryllium. A certain number of ionization energy is absorbed, and this electron now has enough energy to fly away, and now you have an ion of beryllium with a +1 charge because it has 4 protons and 3 electrons, so that's a positive charge. Now, after that first electron is taken away, you could take more energy to remove a second valence electron from the atom, right? So that's called the second ionization energy. So whatever amount of energy is required to take the second electron away and produce a beryllium ion with a +2 charge, that's the second ionization energy. So we can see here the equation for second ionization energy. You start off with a positive ion in its gas state, and then once the electron is removed, it's still a positive ion, but it has a +2 charge. And you might notice here, as the electrons get taken away, your atoms get smaller and smaller. Not by much, but there's a slight decrease in how big this atom is. Why? Think of it this way. Originally, beryllium has 4 protons and it has 4 electrons, right? So protons and electrons, their relationship to each other is an attractive one. So protons are pulling the electrons in towards it. That's why the electrons are staying attached to this atom, just like we are staying attached to the Earth because of gravity an attractive force holding us onto the earth, electrons are staying attached to this atom because the protons provide an attractive force holding those electrons on, right? That's the electrostatic force of attraction between positive and negative. However, there's 4 electrons here. How do electrons feel about each other? They're negative. So negative repels negative. So the electrons are being pushed away by their neighboring electrons, but they're being pulled in by the protons inside the nucleus, right? So there is a delicate balance of push-pull, and the electrons remain on the atom, but they don't fall into the nucleus, right? There's a certain balance. So that's with the neutral atom. So once one of these electrons is removed, now you have this beryllium ion. There's still 4 protons in there holding the electrons in. There's still the same attractive force, but there's not as much repulsion. Electrons aren't being pushed away as much because where there were 4 electrons pushing each other apart before, now there's only 3. So those electrons can now get a little bit closer to the nucleus than they originally could. Right? Once you take the second electron away, now there's only 2 electrons pushing each other apart. So now they get even closer to the nucleus than they originally were. So you can have a first ionization, a second ionization. You can also have a third ionization. And this third valence electron can fly away to give you a beryllium 3+ ion. However many electrons you have, that's how many ionization energies you can have. Not that all of those ionizations will actually happen, because as you move forward, it's harder and harder to take those electrons off, so more energy is required. It'll get to the point where some electrons are so difficult to remove, they require so much energy to remove, that they're just never removed in reality. Okay, so let's write an ionization equation for aluminum in this case, right? Because you might be asked to do this. So in an ionization equation, aluminum going from a neutral atom to having a charge of 3+. So you'll get the symbol for aluminum, which is Al. It's going to be just a gas form, right? And then ionization occurs. Now you've created an atom with a +3 charge. So that's Al + 3, still in its gas form. How did aluminum get a charge of +3? It lost 3 electrons. So you signify that by writing +3 electrons on the side. This doesn't mean 3 electrons have been added. That means 3 electrons have been released, right? These 3 electrons are now separate from the aluminum. If you were to write equation for the reverse process, something gaining an electron, that electron will no longer be on the product side. The electron will now be on the reactant side. So chlorine gas, gaining 1 electron results in a negative ion of chlorine with a -1 charge, still in its gas form. Okay, so let's talk a little bit more about ionization energy. So second ionization energy is always higher than the first for 2 reasons that I touched upon already. Right? Once an electron has been removed from an atom, a positive ion is created. The original atom that the electron was on was neutral, right? And the new positive ion that's created has a positive charge. This positive charge attracts a negatively charged electron more strongly than the neutral atom did. So where originally you were removing an electron from a neutral particle, now for the second ionization, you're removing your electron from a positively charged particle, which we know that the electron is more strongly attached to. Therefore, you need more energy to remove the second electron. You need a higher ionization energy. Second point, once that electron's been removed, there's less repulsion between the remaining electrons. Those remaining electrons, instead of being far out, they're pulled in a little bit closer to the nucleus. Once they're closer, they're more strongly attracted and more difficult to remove, meaning they require more energy to remove. Think of a magnet on a fridge, right? The further away the magnet is from the fridge, the weaker that attraction is. Once the magnet is close to the fridge, that's when the attraction is strongest. Okay, so here comes the math portion of this. All right, so before we talk about that, let's revisit this diagram over here, this energy diagram for hydrogen. Right, we see here energy transitions as electrons drop in energy level. So all the drops down to energy level 1, the ground state, releases UV light. Drops down to the second energy level, releases visible light. Drops down to the third level, releases infrared. So that's light being released as electrons drop. But the reverse can also happen, right? Electrons can jump up to higher energy levels as light is absorbed. So if an electron is on the ground state and it absorbs UV light, it can jump up to whatever energy level matches that amount of energy, right? Electrons on the second energy level, when they absorb visible light, they can jump up. So whatever exact amount of energy is absorbed relates to where the electron jumps to. And if an electron absorbs just enough energy, it will go beyond energy level 2, 3, 4, 5, or 6. It will go to what we consider the infinite energy level, meaning far enough energy to jump off the jump off the atom entirely. Right? So at that point, the electron has absorbed enough energy that it entirely leaves the atom, producing an ion. That is what ionization energy is. How much energy has to be absorbed for that electron to leave. Let me show you a quick visualization of this before we talk about math. So here's a simulation of a Bohr diagram for an element. Right, you have your nucleus at the center. You have your nucleus at the center, right? That's where your proton is. You have energy level 1, 2, 3, 4, 5, 6. This electron is hanging out in the ground state, right? That's the lowest energy, that's the most stable state for the electron to be. However, if I turn on this white light here, and so if I turn on this white light here, and remember, white light is actually all the colors on the spectrum, right? And now I see that photons of light are passing through this atom, going through mostly empty space, but some of them will hit and energize, will hit and excite an electron. And depending on what kind of photon hits an electron, whether it's UV, visible light, ultraviolet, it will jump up to a specific energy level. Right? So you can visually see the electron jumping as it absorbs light, and you can also track that down here, the transitions in energy level. And you'll also see sometimes there's photons of light flying out. That indicates an electron has dropped in energy and it's released light. Right, so here we can see the energy levels directly. So this electron has just jumped up, it's dropped down all the way to 1. So that's what the electrons are doing, right? They're transitioning from energy level to level based on photons of light being absorbed and released. Okay, so what is the energy of a photon? If you recall, we said the energy of light is related to the frequency of that specific wavelength, and the frequency and wavelength of that light. All right, so the equation, E equals hv. Energy is equal to Planck's constant times the frequency of light. So if I give you the frequency of a certain frequency of light, and I ask you to calculate what the energy what the energy contained in it is, all you have to do is plug in Planck's constant and multiply it by the frequency that I've given you. Planck's constant is not something you have to memorize. This equation is not something you have to memorize. These are both in your data booklet. So let's take a look at that real quick. So your data booklet has a bunch of useful equations in it, right? And it's listed by topic. So topic 2.2, That's when we learned about light, right? The speed of light is equal to its frequency times its wavelength. We also have here topic 12.1, energy is equal to Planck's constant times its frequency. You don't have to memorize these equations. You just have to know when to apply them, know where to find them in here, and know what these letters are, what these symbols mean. All right, C equals speed of light. This is your frequency, and this is your wavelength. H is Planck's constant. Are you expected to memorize Planck's constant? No. If you scroll down to the second page, here's a bunch of physical constants and unit conversions that you do not need to memorize. So one of those is speed of light is right here. Planck's constant is right here. So during any short answer questions on the IB, you can always refer to this. So if you're calculating energy of a certain frequency of light, Planck's constant times frequency. That's it, right? It's simple, just plug and play. However, some questions may not give you frequency. Some questions may give you wavelength instead. So that may be a two-step problem. In that case, you take your wavelength and you plug in wavelength and speed of light to figure out frequency using this equation that we learned earlier. So let's do a couple of examples. All right, so first one, what is the energy of microwaves if frequency is 2.45 times 10 to the 9th power? Right, that's how many times, how many waves you have per second for microwaves. So the first thing you do, you have to recognize this is an energy and frequency question. So you'd find this equation unless you just know it. Energy is equal to Planck's constant times frequency. Right? Get the equation, plug in what you know. You know Planck's constant. You know the frequency. Plug it in and answer it. So I'm going to show you what this will look like on your calculator. Right? Make sure whenever you have a large number with exponents, protect it with parentheses. Because based on your calculator, if you don't have the parentheses, you may get weird errors. You might have a good understanding of the problem. You might understand exactly what to do, and then you get the wrong answer on your calculator, and that would just be unfortunate. So make sure you get practice doing this. And once you plug it in, you'll see that your answer that you get is 1.62435 e negative 24. How do you write that? Like this, right? So this e over here stands for times 10 to the whatever power. And did I round this wrong? I rounded this wrong. So this should be 1.62. Let me cross that out. 1.62. So why did I stop at 1.62? Why did I not write 435? Because the number I input has 3 significant digits. So my answer that I write down should also have 3 significant digits, right? 2, 4, 5, that's 3. 1, 6, 2, that's 3. I don't want to put any more numbers because that would imply that I know my answer with a greater precision than I actually do. Because these numbers at the end are no good because I don't have that many significant digits in my inputting number. All right, so let's try problem number 4. What is the energy of ultraviolet light if the frequency is 4.72 times 10 to the 15th power? Again, figure out your equation, plug the things in. All right, try this. Put me on pause, try this, then hit play and check your answer. Do the same thing for 4, 5, and 6. All right, I'm assuming you've tried this. You've tried all the problems yourself. So let's go through the answers right here. All right, very straightforward. Just plug and play. Okay, so now let's go to a more complicated version, not too complicated, but a version that requires one more step. What is the energy of radio waves if the wavelength is 3.11 times 10 to the 2 meters? So here I can't use this equation, right? Because wavelength isn't in here. The equation I would use to find energy is equals Planck's constant times frequency. I know Planck's constant, but I don't know frequency. So I want to calculate that first. How do I calculate frequency? Well, you know this equation here, or if you don't know, it's in your data booklet. So this equation, speed of light is equal to wavelength times frequency. However, right now, speed of light is isolated on one side. I'm not interested in speed of light. I want to know the frequency. So I'm going to isolate frequency, right? So to isolate frequency, get rid of this wavelength that's over here, right? That'll get rid of it on this side. Cancel out, cancel out. So now I see that frequency is equal to speed of light over wavelength. This equation over here. All right, so now I know how to calculate my frequency because I have wavelength. So speed of light divided by wavelength. Here's my frequency. I've got this. Now I can plug that in here. Multiply. There's your answer. But that was a lot of steps. All right, there is another way to do this. So if you're comfortable with manipulating equations and plugging one equation into another equation to kind of find yourself a shortcut, I will show you another way to do it. If you find that way to be complicated and you think it will not help you, then don't worry about it. You can just do it this way with 2 steps. So how do I do this with fewer steps? I can make a new equation. Right here, I have E equals H times V. Here, I have V equals C over lambda. So if this and this, if they're the same thing, I can just replace this. Right? If they're the same thing, I can just write one instead of the other. So now I have a new equation. Why do I want this new equation? Because H and C, they're just numbers I can plug in, already given. And wavelength is what I've been given in the problem. So that's also a number I can just plug in. And so I have this, multiply the top 2 numbers, and divide by what's in the denominator. All right, so why don't you try problem number 8? Okay, I'm assuming you've tried it. Here's how you get the answer. And just a tip, sometimes it's easier to do the multiplying first, right? Multiply the numerator and then get your answer and then divide it. Doing that in your calculator in 2 steps can minimize issues. Okay, so here, this is a IB question, a 2-part question. The first part, so this says the lines in the ultraviolet emission spectrum of hydrogen gas, it will converge at 9.12 times 10 to the negative 8. What does that mean? It means that here your lines are pretty far apart, right? Your emission spectrum lines are pretty far apart. And as you get to the UV side, as you get towards 9.12 times 10 to the negative 8, they're converging. The lines get closer and closer together until they're basically on top of each other. Right, so using this, by knowing what wavelength the convergence happens, you can know what energy, what amount of energy that's related to. And that will tell you the ionization energy. So how do we do this? So energy, right, we'll use our combined equation. If you don't feel comfortable using the combined equation, you can do the 2 separate steps. But energy is equal to Planck's constant times speed of light divided by wavelength. Plug all the things in, right? And then here, 9.12 is basically, you're seeking where the convergence happens, right? Convergence happens on this side, and we see that the limit is at 9.12 times 10 to the negative 8. The information was given to you here, but if it wasn't given to you, you should be able to figure out by looking at where the limit is and what the units are. So plug it in, calculate, and that's how much energy is required to ionize hydrogen gas. But this is in joules, right? That's how many joules. Joules is a unit. It's asking in how many kilojoules. So you just take that, divide it by 1,000 to convert to kilojoules. That's like saying I've got 1,020 meters, right? How many kilometers is that? That's equal to, you just divide by 1,000, 1.020 kilometers. So when you take a unit of anything and convert it into a kilo, like take a meter, convert to kilometer, gram to kilogram, joule to kilojoule, you just take your number and divide it by 1,000. Okay, the second question. Explain why the convergence line in the ultraviolet spectrum must be used to calculate ionization energy, rather than the convergence line in the visible spectrum. So this is n equals 1, right? N equals 2, n equals 3. And we said jumps from here is UV, jumps from here is visible, jumps from here would be IR. So it would be a jump from here to wherever infinity is, n equals infinity. That's the amount of energy that's required to ionize an atom, right? From all the way down here to here, not from here to here, right? So you need to get the transition from the first energy level to infinity to know what the ionization energy is. Visible light isn't from the first energy level, it's from the second energy level. Okay, well, that is it for today. Talk to you all next time.